Okay, good morning, everybody. I hope you guys slept well and, you're ready for this day. So, anyway, I've been working very hard on your worksheets, and so I got to go back and remember which ones we did here. So, what we're looking at now today, if I go to the browser here, all right, we go to the browser. Here we are. We look for Calculus 2. And I think, online transition. Down here, we looked at parametric equations. And, parametric, this is the lecture. We're looking today here, we just looked at the curves yesterday, and we really just learned two things. Curves can be described parametrically for our benefit. And they also can have initial points, terminal points, and an orientation. So that's going to be useful for us today. And so if I look at this is, again, some more worksheets that I developed for you guys. And what you guys see here is that you see the equation here of a parametric, the format x is f of t, y is g of t, t is in an interval. And we like to determine today, the derivative of a function x that is described by that curve C parametrically, right? So we have a curve here still. So let's see if we can try to enter this into, let's go to the iPad and then try to see if we can enter this here, see how this turns out. Okay? And I'm looking at that, and yeah, sure enough, we do have this here. So here's what I'm talking about. This is a curve. I did not use and I do not use y equals f of x. So you guys know, because f is taken here already. So let's get that out of the way. So we can't use that. So what we are doing is, here's our parametric curve, at least the equations in general. And what we're still looking for at a particular point here, right? There's an x coordinate, there's a y coordinate, there's some t value though. So for some t, we are at that point. We want to find dy dx. Okay, because we're going to do all the familiar calculus kind of things with this. So we can find, where the function's increasing, where it's decreasing. We can find where there's horizontal tangents for this curve, vertical tangents, all those nice things that we know and love. Now, here's what I derived for you guys, and I do it a little bit different than the book. I give some sort of middle steps. It's equivalent. It's the same thing, but here's what I want to remark here, right? Here's the proof, really. And I'll try to make that. There we go. Here's the proof. Remember, we can't use y as a function of x because f is already taken. That letter's taken. Okay. So when we want to find dy dx here, and we have, parametric curves here, here's what I actually did for you guys. I let y here, see this variable? We let that y, I just called it g of t because that's what y is, right? You go back over here, y is g of t. You guys remember? So y is g of t, and we're going to differentiate with respect to x. Now, all we really have to use, ladies and gentlemen, is chain rule. Okay, chain rule is the key here. So by chain rule, we get g prime t times dt dx. This is the chain rule portion. And then you say, well, what is the definition of g prime t? Well, that's simply dy dt. And that's still times dt dx. Okay, so double check here. This is where we're at. And then this is a product. So I wrote our product here, so you guys know, as a quotient. So there's a product right in here. And let's change that color. We got a nice product. And I wrote that as a quotient. And it's a little too big. So we wrote that product as a quotient. And what you end up with is the definition of our derivative. Okay, so we have that dy dx becomes really dy dt over dx dt. So here's a derivative here. I want you guys to notice something kind of interesting. We have over here the definition of dy dx. And notice you say, but Mr. Judge, don't these cancel when I'm left with dy dx? They do, but this is chain rule. Remember that? That happens with chain rule. So the key to this demonstration is really just chain rule, using the definition. So we have a way now so that we can actually perform a derivative, find dy dx in the sort of rectangular coordinate system. That's what you're seeing here. Right? You see the x value and the y value, but things are defined parametrically. For some t, we're at a point. We want to find the derivative at that value of t and do all the nice things we know and love with calculus. So I'm going to go to an example straight today and say, okay, let's see if we can find something kind of interesting to find the derivative of. Let's look at this curve. We could define it this way, e to the square root of t, y equals and I have to double check what this is. This is t minus. Got to double check. I'm going to take some of these things from your book. Make sure that that's natural log of t squared. Yeah, it looks like it is. Okay, and here's my parametric equation. T is 1. So I often just say PE for parametric equation here. Now remember, we want to determine the derivative, meaning dy dx. Okay, so let's find this derivative here. And you guys know, every time you use a formula, I recommend you write it down. So this is dy dt over dx dt. All right. Okay, so let's start this off. Now remember, we have to go here and differentiate. We need dy dt. That dy dt is our numerator. We didn't want to do that. That's our numerator. So you can say, let's put it maybe right here. Dy dt is that derivative with respect to t minus natural log t squared, which is going to be d dt. If you guys remember, this is going to be, let's do it this way. 1 minus 1 over t squared times 2t. There's a chain rule there, right? So this is 1 minus, looks like 2 over t. And that's dy dt. We also need dx dt. All right, so you say, okay, how do we get dx dt? Well, dx dt is now the derivative with respect to t of this function. And that's e to the square root of t. Now, this is going to be e to the square root of t times the derivative of that square root of t by chain rule. So don't forget your chain rule. And then this derivative is really 1 over 2 square root of t. You guys remember, like I said, some of those derivatives you really want to remember. You know, they come in handy. Right? They're kind of memorized there. Okay, so that's our dx dt. Now, all together here, because remember, we have to take both of these terms and we have to divide. So you have dy dx becoming 1 minus 2 over t over really e to the square root of t over 2 square root of t. Okay, so, I mean, this is the derivative, but you have a complex fraction, right? And you say, what do I do with complex fractions? Well, you got to simplify, do some algebra. So when I simplify this, I'm going to replace this 1 with t over t, and that's minus 2 over t. And I'm going to multiply. You say, what do I multiply? Well, okay, well, if you want to see every detail from the algebra, you really divide by e over square root of t, 2 square root of t, which comes out to be multiplication. So you're going to have t minus 2 over t times 2 square root of t over e square root of t. So let's see what our dy dx becomes. This is the derivative. 2 square root of t minus 2 over t e square root of t. Now, I'm just trying to double check to see if we made a mistake anywhere. There can be some more. We can simplify some more here, by the way. If you guys notice, I can say square root of t, cancels, and here's what you can get. 2t maybe minus 4 over the square root of t, e squared of t. Now, in some sense, this is the derivative. I mean, not in some sense. This is exactly what the derivative is. This is using the definition that we have there for you. And let's make sure we have a nice x. That's how you find the derivative. But I want to note here, you said they gave me a t value. So let's note. What if they told you they want dy dx at a location? Now notice they didn't give you a point P. They didn't give you an x and y coordinate. What they gave you is a parameter value. In this case, t is 1. Now, when t is 1, you are at a location. Okay? We don't know what that location is because we didn't punch the numbers in. If we want to know, I'm just saying, let's know. If we want to know the location, you say, well, how do I find the location? What's the x and y coordinates? Well, plug in t is 1 then. So if t is 1, we go here, we go here, we go here. The x coordinate's going to be really e to the square root of 1. Or we say x is really e. The y coordinate's going to be 1 minus natural log of 1 squared. We know this will be 0. So the location, the point that they're talking about is e, comma 1. This here is the location of the point. Now, I'm not going to draw the curve out, but I could. I can't, I can take a look at what this curve looks like. It's not the point. But this is the x and y Cartesian coordinate version of a point on our particular curve here, right? So you go, oh, okay. This is the point that we're talking about that happens for some t value. And in this case, the t value is 1, right? So here we go, okay, t is 1, and then here's the coordinates of it. So that's explaining to you the little details. So I say, okay, fine. We know the location, e is 1, and I'm going to put that word here. Location. But how do you find the derivative, dy dx, for a value of t? Very simple. Plug in t. T is 1. So my derivative becomes 2 times 1 minus 4 over square root of 1 e to the square root of 1. Or we can say the derivative here is going to be negative 2 over simply just e. So here's an example of how you find or how do you use that derivative formula here. And I found dy dx. We found this value when t equals 1, or let me do this again. This is good for when t is 1 or at the point e comma 1 in the Cartesian coordinate system. Okay, so that's kind of where we're at. So we're looking at these fancier curves and we're finding the derivatives at various parameters. And so here's what you guys get here. Okay, now I want to remark about something here, so let you guys know. Go back to the curve because this is going to be an issue. I want you guys to notice something here. I'm going to give you another note because once you find derivatives, you can find, there's certain other things associated with the derivatives. And they can say, by the way, and I'll do it this way, by the way, what is the equation of the line tangent to the curve when t is 1. Here's a nice by the way statement. In other words, now that you found a derivative, how do you find the very famous things like equation of a line tangent to the curve, right? This is calculus 1 business, right? If you guys remember, equation of the line tangent to the curve, this is also an algebra question. Because to find an equation of the line, we use the equation of the line formula. Y minus y1 is m times x minus that x1. So if you guys remember that, we can find here from algebra, this is going to be the point slope form. And because this is a calculus question, what changes here is just this. This is m tangent. Okay, so we have m tangent. Since this is a by the way question, we're using the same setting. We're finding the equation of the line tangent to the curve when t here is 1. Now, this is why you need to know the locations here, because this happens we looked at when t is 1, we got the x coordinate and the y coordinate. So this is my x1, y1 from algebra and calculus. So algebra and calculus. So ladies and gentlemen, y1 is 1, x1 is e. And what you end up with now is you say, oh, okay, I get y minus 1 is really m tangent, x minus that e, but what is m tangent, right? And this is what they need. This is what they want to know, right? M tangent was that dy dx when t is 1. In other words, you found the derivative at the point for the parameter value t is 1. And we said, well, what was that? We forgot. It's way over here. It's -2 over e. So here's a nice by the way question. -2 over e gets replaced here, and the rest is just algebra. So you say, okay, y minus 1 is -2 over e times x minus the e, or y minus 1 becomes -2 over e x. And you can say, is that going to be plus 2? It looks like, because there's an e there, right? So minus and minus makes that a plus. Okay. And now we can add 1 to both sides. You're solving this with algebra skills. And you end up with y going to be -2 over e x plus 3. So here is the equation of the line tangent to the curve at the point E1, or when the parameter value t is 1. So this is how we use a derivative, ladies and gentlemen. Okay, this is how we find that derivative and how we use it. I want to go back again and remark something here. Here's another remark. Here's another by the way. So, what is the location of a horizontal tangent? And go back again to where you have horizontal tangents, right? We mean dy dx equals 0, which implies, if I go back to the definition, see if you guys know what that means. Go back to the definition of what this derivative is. If this is equal to 0, since we have a fraction here, right? We have this equal to 0. We can go maybe over here. Yeah, this is where it was. Okay. If this is 0, when is a fraction ever 0? A fraction is 0 only when my numerator is 0, but the denominator can't be 0. So that means to have a horizontal tangent, dy dt must be 0, but you can't have dx dt. That can't be 0. You can't have 0 over 0. Okay, remember we don't divide by 0. So horizontal tangents happen when dy dt equals 0. So I'm going to write that down here. It's horizontal tangent. Similarly, we say that happens when dy dt is 0. HT, horizontal tangent. All right, this is what they asked us. What about, since I'm on the, I'm talking about the topic, what about? Vertical tangents. VT. Well, vertical tangents happen again when the opposite is going on. The denominator will be 0, but the numerator can't be 0. We're now going to focus here on the definition of our derivative. This happens when my denominator is 0, remember? But my numerator cannot be 0, so it's going to be the opposite. dx dt is 0. But dy dt can't be 0. Okay, so you're going to have here when dx dt equals 0, and yeah, dy dt can't be 0, but anyway. So, I mean, if we want to go to the original question here and we say, okay, what was the parametric curve they gave us, right? Where are the vertical tangents? Where is the horizontal tangents? You're going to go to this derivative right here. You already found that. All right, let me see. Go back here. Yeah. Right? You got dy dx. This is a fraction here, or we should go here. Where is this here? Okay, let's actually find these. We could go there. We could go over here. We need for horizontal tangents dy dt. So we say, what is dy dt? Dy dt was, where are we at? That 1 minus 2t. 1 minus 2 over t, which we found was t minus 2 over t. So double check this idea. And that means if we set this equal to 0, right, dy dt is 0, that implies that t minus 2 has to be 0, or that t is 2. So when t is 2, we have a horizontal tangent. Be careful here, though. I want you guys to really be aware. Go back to the curve, and here's what I started to remark. This curve here, ladies and gentlemen, is defined only for t being greater than or equal to 0. So let's be careful here with that. Let's write that nicer. And then you say to me, why does that have to be greater than or equal to 0? Well, you're taking the square root. We don't take square roots of negatives. And should it equal 0? What happens if it's 0 here? You got 0 squared is 0. We can't get natural log. So that's not even it either. So we're going to have to look at the domain here because it has to satisfy both. T can't even be greater than or equal to 0. If I only look at the x coordinate value, this one, I have to consider this. Right? So remember, we have the natural log of 1 is 0, so that means we have to remove the equal to 0. So it has to satisfy both the x coordinate and the y coordinate, meaning it has to be defined on the curve. So you need to consider this when you're looking at some of these. Okay, it has to be defined on the curve here. So t has to be greater than 0, not greater than or equal to, because natural log won't be defined. So when I find a horizontal tangent, when t is 2, that's legitimate because I know t has to be strictly positive. All right. Okay, and now you say, well, what about dx dt? What about This problem, well, if we look at this question here, we got to find where dx dt, what is dx dt anyway? Oh, it's, yeah, we know t can't be 0. So here's my dx dt. Okay, so if I write that down here, let's write that down, dx dt now. Looks like that's e square root of t over 2 square root of t. That has to equal 0. So if dx dt is 0, that means e square root of t over 2 square root of t is 0, which really implies e to the square root of t has to be 0. Now, you guys know this never happens. And you say, why does this never happen? Well, it never happens because this function never crosses the x-axis. So there is no t. You can't come up with a t value that you plug in here that makes this equal to 0. So that means there is no horizontal tangents. It has a vertical no vertical tangents. It has a horizontal tangent, but no vertical tangents. So this is all the information that they can ask you and also give you a nice remark since we're on the topic of, oh, what was this horizontal tangent? Let's go back down here and ask you another question here. This is when t is 2, right? What is the location of the horizontal tangent? You don't have a vertical tangent, but you may have a horizontal tangent. It happens when t is 2. So you say, how do I find that location? You find that very easily by letting t equal 2. So you have to go all the way back to the original questions here, or the equations, parametric equations here. We said, okay, x is e to the square root of t. Y is t minus natural log of t squared. T being 2 is allowed. It's in the domain. So we can put 2 there, 2 here, 2 here. Here is the location, ladies and gentlemen, of the horizontal tangent. It'll be e square root of 2. 2 minus natural log 4. Here is the location of what they're asking for. Oops. And I want to emphasize this. Location means address. All right. This is the location. The x and y coordinate. So there's a lot of calculus that comes into play once you know how to do a derivative, and that's kind of the thing here, okay? So you have doing a first derivative. All right, and I'm kind of curious here. Let's hopefully we go back. Let's go back to the browser here, and I'm going to try something here for you guys here, okay? Let's try to take a look here. See if we could do this. I'm going to put E, and then that's going to be 2. A power, it's a square root of, and I got to find the parameter t. Okay, I think that was our first, yeah. All right, now I'm going to come out, and I got to put a comma here. Oops, I'm not out. Put a comma, and that's t minus natural log t, and that's going to be raised to the second power. Put that second power here, and it can't be 0. And let's change that value. Let's say 6. Okay, so you guys could get a nice kind of view of the curve. So what they're saying, let's see, I might have written this wrong here. Okay, no, I think we're good. We're good. As you guys can see here on this curve here, we're fine. Somewhere over here, you can't see we have a horizontal tangent, right? and there's no vertical tangents. We have a horizontal tangent. And so this is that curve they're talking about. So I wanted to show you guys that. At the location e square root of 2, 2 minus natural log 4, at that location, x and y, we actually have, ladies and gentlemen, horizontal tangent. So if you plug in those coordinates that we just did, you'll find out the details there. Okay, good. So I just wanted to throw that out. And notice another thing I wanted to say here. There are intervals where this function is increasing and decreasing. Wait a minute. What about that? Hold on. First derivative. Let's write this down. Let's say iPad. Here we go, iPad. What about when the curve now, we'll call curve C, is increasing and decreasing? Wait a minute. Here's what they really mean. They're going to, for what t? So when do you have increasing, decreasing points on a curve? For what t does that happen? We got to remember our calculus 1. Well, dx, the function, we have dy dx has to be greater than 0, and that means we have an increasing situation, and we have dy dx is less than 0. That means we have a decreasing situation. Okay, and they want to know for what t, so I have to get my hands on that derivative function, and you say the derivative function, dy dx was, let's go back and find out what it is. Oh, dy dx, where were you? All the way over here. Oh, is it? Nope. Dy dx, there it is. 2t minus 4, square root of t, e square root of t. All right. 2t minus 4, the square root of t, e square root of t. So if we're going to find, ladies and gentlemen, the intervals of increasing, decreasing, really they're looking for the value of t for you have increasing, decreasing. Because this here, remember, is a formula in terms of t, right? So increasing, decreasing. If you guys remember, it's sign analysis on that first derivative. Right? Sign analysis. So we're going to have to do sign analysis, yes, on the first derivative, but it's in terms of t. Because we have to find where it's positive and where it's negative, right? Increasing, decreasing. Positive, negative. So if you guys remember your sign analysis tools, right? You have a rational. You find, first of all, the first part of it is set the numerator equal to 0. Find the zeros, right? Solve for t. And you go, okay, 2t is 4. And then get t is going to be 2. The second part is the square root of t, e square root of t. Let that be 0. And then we say again, oh, that never happens. Right? Good. So we're going to set up our real number line in terms of the variable t. And I got to remark, this happens when t is 0. This is dy dx. But this is what's going to happen. Let's remember the domain. T has to be positive. So maybe over here, we're going to put a 0 just to say we can't have negative. It can't be 0 and it can't be negative. So we're going to do our sign analysis here, and we have to notate our intervals. So we only have one region, 2 regions here in this problem. But remember the domain of t. That's where people will make a mistake. And again, you guys know, get some test points. Not negative 1, positive 1. We just got through talking about that. Positive 1's a test point. And then maybe you can say, I don't know, positive whatever you need. 4 maybe, I don't know, 3, 4. Whatever. This is not to scale. 5 is a test point. Okay, these are test points again. We're going to test those. You say, what am I going to test? Well, you got to go back and put them in the first derivative. So when t is 1, you guys already know what will happen if t is 1 here, right? First derivative. The denominator is going to be positive, so we only care about the numerator, right? Square root of 1 is 1, e to the square root of 1, that's e. So this is 2 minus 4. This is a negative 2 over e, I guess. The point is it's actually negative in quadrant 1. These are the t values. If I plug in t is 5 now, again, you could kind of ignore the denominator because it's going to be positive, right? Square root of 5 is positive. E to the square root of a positive is positive, but the numerator is not, because 2 times 5 is 10. 10 minus 4 is going to be 6. So region 2 is positive. So yeah, you do sign analysis on that first derivative just like before, but the variables now are different. It's t for your parameter. This isn't the location. These aren't values of x. So they're going to say, for what t do you have increasing, decreasing, right? Well, for what t? Here's your final answer. The curve is increasing, read the interval, for t greater than 2. Because that's the interval you're in here, t bigger than 2, right? And then you can also say the curve is decreasing. And you say, when's the curve decreasing? Well, for values between 0 and 2, right? You have to be between the 0 and 2. These are t values, parameter values. And that's pretty much it. That's it for the first derivative. So here's how you get a derivative. Here's how you handle that derivative. Ladies and gentlemen, this is where you're at. This is talking about just the first derivative. And if you go back to the curve, you know, it's not values of x. Here's that curve again. Let me see if I can. There we go. There's the curve. This isn't values of x. These are parameter values here. You could just see the curve is actually a decreasing, increasing curve. So at some point, really some parameter t, this will actually start to increase, right? When t is 2, we have a particular x and y coordinate. Now we have an increasing function. So if you say, okay, Mr. Judge, what comes next with this? Well, here's what the next question is going to be, right? What about the second? What about the second derivative now, right? The second derivative meaning d squared y dx squared, right? What formula can we use for the second derivative now? Because for the second derivative, you have points where you have what's called concavity, right? Concave up, concave down, points of inflection. Started to talk about that, inflection points, and concavity. So, okay, we need a way to look at the second derivative. So if I look at my sheet I did for you guys here, we're starting to talk about that. The second derivative can be found similarly. And here's what I do, though, to find the second derivative for you guys. Here's the second derivative formula. I want to point out something here. I say let dy dx. Remember, this is the first derivative here. dy dx. Let me undo that. Here's my, that's not what I want. I want the highlighter. Here's dy dx. It was a function of t, remember? So dy dx is a function of t. That's the key. Now you wrote that in words. It's a function of the t variable. You guys seen it by the last example. So when I use the definition of the second derivative right here, that's the derivative of the first derivative. Okay, derivative of the first derivative. I got to plug in. Here's the derivative of that first derivative, u of t. And again, you say, oh, by what? Chain rule. By chain rule, you have du dt times dt dx. That's chain rule. And then I wrote the product as a quotient. So I have du dt in the numerator and then dx dt in the denominator. I just wrote a product as a quotient. And then I put back in what u really is. What was u to begin with? U is actually dy dx. This is u. And this down here is still dx dt. So in your book, when you say, okay, what about the second derivative formula? Well, this is what comes up in the second derivative formula. Okay, that's how you handle this. So we got a way to get the second derivative now, but you need the first derivative. All right, so let's show you guys here how to get the second derivative. So if I write it down and I say, okay, how do we get the second derivative, right? D squared y dx squared is, it's going to be d dt of that first derivative, dy dx, over, again, dx dt. X, again, was, I think it was e to the square root of t, and y was t minus natural log t squared. But in order to find the second derivative, I need dy dx. That was the function of t that we had. So the function of t, it was way back over here. This is right here. Let's kind of erase this here so we can say, oh, here's what it was. 2t minus 4, and we got this down here. Ooh, okay. 2t minus 4 square root of t e to the square root of t. Okay. So this goes here. 2t minus 4. The square root of t e to the square root of t. Ooh, that would go in here. And then you said to me, what about dx dt? Well, what do we find for dx dt? I guess we could do it again. We're right here. This is going to be, right? What was that? That's e to the square root of t, and then by chain rule. So it's e square root of t over 2 square root of t. So if you had to find this, here's what you would do. You differentiate 2t minus 4 over the square root of t, e to the square root of t, over, that's just e square root of t over 2 square root of t. Okay? So this is what you'd have to differentiate. And again, you're going to have to use quotient rule, right? Quotient rule for derivatives, QR. And that's going to be, something kind of very interesting. There's going to be a lot of algebra there. All right? So now I pulled this question out of the hat, and I want you guys just to remember a few things. When do you have concave up? Concave up happens when that second derivative is positive. And when do you have concave down? Well, that happens when the second derivative is negative. If you guys remember from Calculus 1, when do you have an inflection point? Well, inflection points happen when you change concavity, right? So you say you have to change concavity. And it has to be a point on the curve. So t has to be in the domain of your parametric equations. That'll give you a point on the curve. So I want to remark here, this is how we find and use those derivatives. So let me look at another kind of question here, see what we got. Let's give you guys an example here, okay? X is 4 plus t squared, and y will be t squared plus t cubed. And so they're going to say, for what t do we have concave up? And I guess that's all they ask is concave up, but if you know concave up, you can find concave down. So here's another example here. Now, I'm using this example to talk about concavity because it's kind of, like I said, it's from the book, but also you guys have to know, or you should know, a few things. They give you things that you can, differentiate really somewhat easily. That's arguable what is easy to differentiate because, we're all different. But this is why they don't give you all those questions with that one curve. They're going to actually change the curves up like this on you so you guys know. So you guys know if you're going to find where it's concave up, concave down, of course, that's essentially sign analysis. On the second derivative. So that's what you'd have to do, sign analysis on that second derivative. All right, so if you're going to find a second derivative, you need a first derivative. So dy dx becomes dy dt over dx dt. And I can say dy dt is 2t plus 3t squared. dx dt looks like it's just 2t. So double check here, right? dy dt, we found the derivative here with respect to t. dx dt, we found the derivative here with respect to t. So 2t plus 3t squared over 2t. Now, if we simplify this, 2t over 2t plus 3t squared over 2t, you find that's 1 plus, it looks like really just what? 3/2 t. Okay? dy dx. So we're going to use this. And you say, why are we going to use this? Because in the second derivative now, right, if you go to the definition of the second derivative, that's let me write it this way. Right, that's dt of the first derivative over that dx dt. All right, okay, now you say, well, how do we work this? Well, this is 1 plus 3/2 t, right? And what was dx dt? I think it's 2t. Right here, right? dx dt is 2t. Yeah. Replace that with 2t. So you're saying, do I have to differentiate 1 plus 3/2 t, keep that over 2t? The answer is yes. So we get 3/2 over 2t, because this derivative here is 3/2. So what this is 3/2 divided by 2t, or we can say 3/2 times 1 over 2t. So ladies and gentlemen, let's write it down here. That second derivative looks like it's 3 over 4t. Okay, here's the second derivative function. Now, if you remember, since we're going to do sign analysis here, what's the domain on this parametric? They didn't actually give us they didn't restrict a domain, give us values of t, so we have to remember, what's the domain here? T is any real number. Okay, because these are nice polynomial functions, and, you know, they're defined for any real number. So t could be any value. Now that's important to know, because when you do sign analysis here, we want to consider the context, right? So remember, t is any real number. It's going to be a factor in our answer if we don't consider that. Okay, now this is kind of a nice beginning algebra, not beginning, intermediate algebra kind of sign analysis question, right? The numerator is never 0. The denominator is, though. The denominator is 0 only when t is what? 0. So you have a problem here, ladies and gentlemen. Right, so let me change the color. So at 0, that second derivative is undefined. And this is parameters of t. This means I have region 1, I have region 2. So let's use a test point. Remember, t could be negative. That's a test point. T could be positive. And let's kind of make it where it makes some sense to scale, actually. So plug these values in the second derivative. Now, when t is -1, it looks like there's what? The second derivative is negative, because 4 times the -1 is -4, so that's 3 over -4. I don't care about the answer, I just care about the sign. And then I plug in t as 1 here. I get 3 over 4, really, but that's positive now. So, ladies and gentlemen, concave up happens where this is actually positive, and concave down is where my second derivative is negative. So here's our conclusion, right? The curve is concave up for t being greater than 0, it looks like. And the curve is concave down for, it looks like t being less than 0. If you write this in terms of intervals, that's 0 to infinity, and that's minus infinity to 0. But I want you guys to think about this really quick. I'm going to ask you guys, right? What? Just look at this. You guys know what's coming. Do you have, let's say for what t, do you have an inflection point? For what t value? That's the question. You're looking at this information. This information tells you everything. For what t do you have an inflection point? where do you change concavity? Does anybody happen to know? I want you guys to think about this kind of question. As I have you guys think about this, I think I want to try to take a look at this here for you guys. Have some fun this morning. Have you think about that. Where am I going to? I'm going to the browser. Yeah. So this curve, right? This is going to be 4 plus t raised to the second power. And this will be t squared plus t, that's going to be raised to the third power. And I'm going to put like negative 10 maybe to positive 10. And I want you guys to look at this here. Maybe negative, yeah, we'll just do negative 10. Anybody can see something very, very interesting about this particular curve, right? I want to remark at when t is 0 here, you're at 4, 0. Okay, so I want you guys to notice this. When t is 0, you're at 4, 0. Okay, I want you guys to note this stuff. Let me put this down here. All right, t is 0, you're at 4, 0. Okay, so consider everything that we did yesterday and think about t is 0 happens at this point where that first derivative looks like it doesn't exist. It's not smooth at 4, 0. That happens when t is 0, by the way. And notice for negative t values, we're concave down. So I can kind of see the orientation. And for positive t values, we are concave up. So we can answer increasing, decreasing questions here for this curve. But I want you guys to think about this in terms of concavity, because this is something that people will think about. Remember, what's the point where you change concavity? It's the devil's in the details. In order to have an inflection point, ladies and gentlemen, here's what you never want to forget. You're talking about an inflection point. That point, I'm going to write it in red. This must be on your curve. An inflection point is a point that's on the curve. So sometimes students say here, you go, okay, at 0, my second derivative is undefined, right? When t is 0 here. But it's a point on the curve. It's a point where you change concavity. All right, you guys okay with that? So you can say you have an inflection point. That happens when t is 0. That's at 4, 0. Because that's a point on the curve where you change your concavity. So be careful here. You have to double check whether that point is defined. And that's the essence of what, this lecture is about. Now, we just did first and second derivatives here for the calculus. I want to let you guys know we're also going to do area, arc length, and some surface area tomorrow. But I can get you guys started on book work on this section because that's a good idea. And this is the calculus of parametric equations here. So we just started that. So this is actually chapter 11, section 2. So to start, we can say we could do 1 to 19 odd. And let's just start for those. Okay, we'll start today, 1 to 19 odd, and we'll give you guys some more, tomorrow. But I want you guys to get some start on this stuff. Of course, I'm going to supplement with some additional examples, okay, for you guys. I'm going to do that, and you guys know where to look for these additional examples, right? You go to the browser, and you say, I need to go to, those are our notes. You got calculus of parametric equations. The examples are going to go on this side here. Like I gave you examples for arc length and surface area. You guys have additional examples for the calculus here as well of parametric equations. So anyway, I hope you guys enjoyed this today. I know I did. Again, if you have any questions or issues, see me during office hours. Remember, your next test is going to be on this coming Monday. We'll talk a little bit more about that tomorrow, because I got to take a quick pit stop. I had a little too much coffee this morning. So again, if you have any questions, I got to say, sorry, I think I have a department meeting about noon. Yeah, we have office hours from 10:30 to noon, so you're good. Anyway, so if you have any questions or issues, we'll see you in office hours today. I'm going to post some examples, additional examples up online for you guys. But this is the calculus of parametric equations. Okay. Thank you, guys. I do got to run. Sorry.